There we go. So we do have access to the thermo shorts that are on my courses too. So these are kind of condensed, maybe 5 to 10 minute versions of the lectures. So if you go into content, there should be a tab there called Schertzer's Thermo Shorts. So in here for each one of the videos, there should be that sort of 5 or 10 minute condensed version of the lecture. So you can also find those on my YouTube page. Right, so you just click on that and you'll get whatever the link is, right? Also for classes, we'll do problems a lot in classes as well. So here you should be able to click on this and you'll get the starter sheets. So where the long lectures are, there are also PDF documents that are related to the problems that we're doing in class. So here, if you go to my pre-recorded lectures, and then you should be able to see these starter sheets, right? So this is like when you click on this, then you'll see this. I'll work through this page as we're doing the problem. But if you want to have your own records for the problems that we do in class, you can find them here. So we've been talking about thermodynamics and how it lets us kind of understand a little bit what's going on in the universe, right? To do that, we have to divide the universe into two parts. Right? There's the system, that's the part of the universe that we're more interested in. And then there's the surroundings, right? That's the rest of the universe, right? And ultimately, we're going to be asking ourselves 3 questions to solve problems like this in thermodynamics. So the first is, what's inside the system, right? So is it air? Is it water? Is it aluminum? That's going to matter, right? Because different pieces of matter can sort of have different amounts of energy associated with them. Right? Then we want to know, is the system open or closed? That means, can mass come in and out of the system from the surroundings? Right? And the nice thing about the first third of this class is that the answer here is always that it's closed. Right? That it's not open, that mass cannot move between the system and the surroundings. Right? Then we want to know what happens to the system. Right? So in order to find out what happens to the system, we'll be looking here at the first law of thermodynamics, right? And it's got 3 sort of pieces to it, which we'll kind of chunk out, right? And we started to look at this last class, right? So now we have an equation to find the work that's associated with a particular process, right? And then we'll learn some strategies for finding the change in the energy in the system over time. And then we'll use the first law to find how much heat was transferred between the system and the surroundings. That's not always how this problem is going to work, but that's generally what we do in this class. When you take heat transfer, which is another class that I teach, what happens is you'll learn some more strategies for how to find the heat transfer between a system and the surroundings directly. But in this class, typically we'll use the first law to find heat, and then we'll use work is the integral of PDV, and then we'll learn some strategies for fixing states and finding how much energy is in the system at a given time. So this lecture, we're going to start to talk about the first law of thermodynamics, kind of how we can use this equation to solve problems, right? To start to understand what's going on in the universe, right? So we're going to start, the whole first third of this class talks about closed systems, right? So systems where mass is not moving in and out of the system that we're looking at, right? So this, you'd see this in a piston cylinder assembly when both the intake and the exhaust valves are closed. Now, if this piston moves up, then it's compressing the gas. But if the gas is expanding, like after the spark plug ignites, then the gas is expanding and pushing the piston down. And none of that really works if these valves are open, right? Because then this pressure in the cylinder would just be basically the same as whatever's outside the cylinder, right? So we know that a closed system has some fixed amount of mass, right? But that doesn't mean that the volume is fixed, right? Because if we're dealing with gas, which is a compressible fluid, then I can have the same amount of mass in this system, but I move my piston up and down, and kind of the density or the distance between the gas molecules can change, right? So even though we have a closed system, we can still transfer energy between the surroundings and the system, right? Now we have a special kind of a closed system that we call an isolated system, and that means that not only can you not transfer mass, but you can't transfer energy either, right? So you can't do either of those two things, right? So the first law of thermodynamics, right? This is a pretty important thing, right? It's the first law, right? It's the most important thing in thermodynamics. Although when I was taking heat transfer, my old professor would say that there was a thing called the 0th law of thermodynamics, that heat always moves from high temperatures to low temperatures, right? But the first law of thermodynamics is super important. Basically, what it tells us is that energy is conserved, right? Although I guess technically we know that energy can be changed into mass, or that we can change mass into energy as well, but we don't deal with sort of nuclear reactions in this class, even though we will talk about things like nuclear power plants, right? So the first law of thermodynamics is conservation of energy. And I put this up last class, right? The change in the amount of energy stored in the system over some time is equal to the amount of energy transferred into the system by heat from its surroundings, minus the amount of work that's transferred out of the system on its surroundings, right? So this, like I said, I'm not a huge fan of the verbal definition here, right, of the words. I think it makes a lot more sense when we write this as an equation, right? That the change in energy in a system over time is equal to the heat that comes in minus the work that goes out, right? And I also like to draw a schematic, right? So I have this kind of sort of basic sketch of what the universe might look like. We have the system that we're interested in. Over some amount of time, we're moving from one energy state to another energy state. And we can figure out this energy change by looking at how much heat comes in and how much work goes out. And that's really what the first law is telling us. And here, like I said, there's 3 different parts. We need to know the work. We need to know the change in the energy. And with that, we can find the heat transfer. Right? So we talked a little bit about the change in the energy last class. Right? That this change in the energy is the change in all of the different kinds of energy that can be in the system. Right? So at any given time, you can have kinetic energy. You can have potential energy. You can have spring energy, right? Like the energy that's stored in a spring, or we talked about bow and arrows last class, right? And then this new kind of energy that we'll be very interested in this class is internal energy, right? And that's somewhat related to sort of the temperature and the pressure of the materials that we have inside of our control system, right? So we're looking at the change of those things over time. Then we'll want to know the heat transfer, right? Remember, heat in is positive, right? From hip to win, right? That this energy change in the system happens because heat comes in or work goes out, right? And we have this mnemonic device, this idea that, because signs end up being pretty important in this class, right? So we have that the change in the energy in the system is equal to the heat in minus the work out, provided that we have the sign convention that heat in is positive and work in is negative, right? So hip to win, right? Heat in is positive and work in is negative. So conservation of energy is important because, ultimately what this class is about is how does energy change hands, right? If we look at the universe as kind of like a bank, right? Or maybe a financial system, then all of these energy sort of processes we're doing are like transactions, right? So when we, drive our car down the street, we're making a transaction. We say that we have this energy that's stored in chemical form in gas, right? And then we burn that gas. So we make one transaction to turn that chemical reaction or chemical energy into thermal energy. And then we make another transaction to change that heat energy, that thermal energy, into mechanical energy, right? And this class is always going to look at those energy transactions as they happen in the universe, right? So the first law of thermodynamics is super important in this class, as you might guess, right? It's thermodynamics class. And we'll use the first law in just about every problem that we do in the class, right? We'll use it in multiple different forms, but the first form that we'll focus on is this closed version of the first law that we're looking at now. This delta E is equal to Q minus W, right? Now, as we start to relax assumptions, as we start to let mass come in and out, it's still sort of the same idea, right? That we're tracking all the energy that comes in and out of our system. It's just that when we have an open system, it gets a little more complicated because what we'll find is that mass itself contains energy, right? So when we have to track mass coming in and out of the system, we have to sort of account for the energy that it brings with it, right? So now we're going to talk about closed systems, and we're going to use this version of the equation, that delta E is equal to Q minus W. Right? Now, the good news is, right, we already have a way, right, a process for finding work, right? We talked about this last class, that we can find work in a closed system as the area under this PV curve, right? So if we draw, these diagrams are going to be pretty important to us, pressure versus volume diagrams. And the reason is we know that work is the integral of PdV, right? Which means if I can sketch out this PV diagram, then I know that the work done by the process is the area under that curve, right? That's what this is saying. And most of the time, we'll deal with what we call polytropic processes. A polytropic process is a process that follows a rule that looks like this, that pressure times volume to some exponent n is equal to a constant. Sometimes I get a question here, and actually in my notes, I'm not great at being consistent about this, but if you ever see in my notes a V with a line through it, that means that we're specifically talking about volume as opposed to maybe velocity or voltage or some other V, right? So here, if we know that pressure times volume to some power is constant, then that's a polytropic process, right? So if n is equal to 0, right, then this would be P times V to the power of 0. That's 1, right? So this is an isobaric process. Iso means kept the same. Baric is talking about pressure. So isobaric means constant pressure. So if n is equal to 0, then we have a constant pressure process. If n is equal to 1, then we'll see that PV is constant. That's an isothermal process, right? Iso being the same, thermal in this case being temperature, so the temperature stays the same. So Cp and Cv, these are specific heats, different values of specific heat. So specific heat at constant pressure or specific heat at constant value or volume. And if n is equal to Cp over Cv, then this is a fancy word. This is like an engineering decoder ring word, right? So it's going to be an adiabatic process, right? That means perfectly insulated. So that's a process where no heat is lost or gained throughout the process, right? So there's no heat transfer with the between the system and the surroundings. And then we'll have times where n is less than 0. So if n is a negative number, then that means the heat transfer is much bigger than the work, right? So we know something physically about these processes based on the value of n. Right? Now there are some cases, one case in particular, where we won't have a polytropic process. Sometimes the textbook will tell you that the PV relationship is linear, right? So that means that we can construct an equation that looks like mx plus b. Now you could do that and then integrate it if you want, but I would suggest to remember that what we have here is we're looking for the area under this curve. So if you have a pressure volume relationship that's linear, right, then if you drew this, that area would be the sum of the area of the rectangle and the triangle. So if you have a process where it tells you the pressure volume relationship is linear, then what I want you to do is find you draw it out on a PV diagram and just find the areas of the rectangle and the triangle, right? That'll be easier than trying to integrate it. So that's how we find W, right? And that's good because that's one of the 3 things that we need to find in this particular type of problem, right? So now work is now a known thing, right? Based on the given information that we have. The next thing that we'll usually do is find how the energy in the system changes, right? So we know that this delta E is really a sum of all the different types of energy changes that we could see, right? So delta E is really delta KE plus delta PE plus delta SE plus delta U. Now, in the problems that we'll talk about, it's not that kinetic and potential and spring energies are zero. It's that they tend to be really small relative to the change in the internal energy. You know, if we're looking at sort of steam through a steam turbine, it's really the change in the energy of the steam as the temperature and the pressure changes that kind of dominates the problem, right? It's like when we think about the idea of infinity, infinity is not really a number. It's kind of a concept, right? And it's like infinity to me anyway only really makes sense when you're comparing two things, right? So it's like if one thing is really, really, really a lot bigger than something else, then you say, well, it might as well be infinite, right? So what will happen when we use these equations is we'll often end up canceling out delta KE, delta PE, and delta SE. But it's not really that we're saying that they're zero. It's that we're saying that they're so much smaller than delta U that they don't really matter, that you don't have to go through the effort necessarily of finding out what those things are. Right? So some common assumptions we'll use in this class is we'll say things like, oh, the kinetic energy here is much smaller than delta U. So if I took delta KE divided by delta U, maybe it would be less than 1%. Right? So kind of who cares, right? It doesn't really impact the problem that much, right? Same with the change in potential energy and the change in spring energy. These things are often small enough that it's okay to neglect them, right? At least as a first approximation, right? When we're trying to do things on pen and paper to get an idea of what's happening, then canceling these things out is not an unreasonable thing to do, right? And that's always kind of important to remember as engineers. We're not really trying to find the correct answer, right? We're trying to find an answer or a model of the universe that works well enough to give us a solution that's good enough, right? That's safe enough, right? That'll hit whatever benchmarks we're looking for, right? So when we do these things, it's often because we don't know this information, right? But sometimes, I mean, it only really makes sense to cancel it out if it's small enough that we feel like it doesn't really impact the problem, right? So what's the big thing that changes? And in thermodynamics, the thing that usually drives the change in energy in the system is this change in internal energy, right? Or delta U. So that's kind of the most important thing. And if we can make those simplifications or assumptions, then delta E will become delta U, right? Now, if you went through the preliminary lectures, you'll know that delta U, delta big U, right? This is internal energy. We can also write that down as the mass in the system times the change in the specific internal energy, or delta little u. We have this convention in thermodynamics where when we use capital letters, then those are extensive properties that are related to the mass. And when we use lowercase letters, those are going to be intensive properties that are unrelated to the mass, right? So an example of this is density. It doesn't matter how much water you put inside of a swimming pool, the density will remain constant, right? But as you put more and more water into the swimming pool, the volume will change, right? The volume of water will change, right? So volume is an extensive property that depends on how much stuff you have. But density is an intensive property that doesn't matter how much mass you have, right? Now we'll start to talk about how we find this change in specific internal energy next class, right? But right now, if you knew how to do this, then you'd be ready to write the first exam. So basically between now and the first exam, what we're going to learn about is how do we use the first law for closed systems like this? How do we integrate P to dV to find the work? And then we'll spend a lot of time figuring out different strategies about how to find delta U. Right? So just on this slide, it's like this is the whole first exam, which, from 10,000 feet makes it look pretty straightforward. But the problem is there's all kinds of different strategies for how do we find delta U depending on what the material is inside of our system. Right? And then typically what happens in thermodynamics is that we have good strategies for finding the work in a closed system. We have good strategies for finding the change in the internal energy in a closed system. And then we go back to the first law, usually, to find the heat transfer between the system and the surroundings. So that's usually the case, although for the example that we'll do today, it ends up not being the case. But that's okay, because we don't know how to find delta U yet. Right? So we're going to do this example. Right? It says a gas in a piston cylinder assembly is compressed from one pressure at a particular volume to another pressure in a process for which the relationship between pressure and volume is PV to the power of 1.2 is constant. We're told that the mass of the gas is constant at a particular value. And we know that during the process, heat transfer from the gas is 2.2 kilojoules. And then we're asked to find the change in the specific internal energy of the gas in kilojoules per kilogram. And we're told that kinetic and potential energy effects can be neglected. So now I'm going to close this. And we'll do this problem here. Right, so now I've got my problem here. This is my problem statement. So you can find these online, like we said, if you want to look under the long lectures and the starter sheets, then you can find this, right? So first the first part of our problem solving technique is to look for given information, right? So we can see, so it's a piston cylinder assembly, right? So I could draw this, right? When I get to my schematic, maybe we'll get there. And we know that we move from one pressure at 3.4 bar at a particular volume, right? So that's given. We have another pressure. And we know that the pressure volume relationship is PV to the 1.2 is constant. So this is a polytropic process. We're told the mass of the gas, and we're told the heat transfer. Right? So one of the things that I'm going to encourage you to do in this class is to draw what we call state tables. Right? So it's just a handy way, like when you're doing an exam problem, it's nice to have a table like this, because then you can just easily look to see what your information is. Right, so we know that there's gas in a piston cylinder assembly. We know that there's a pressure. Right, now last class, remember I told you if it's a metric problem, it'll generally make our lives easier if we write down the pressure in kilopascals instead of some other unit. Right, so I know that 1 bar is equal to 100 kilopascals. Right, so now at the beginning of the problem, I'm gonna do all this conversion, right? And I find that that's nice in a exam problem, because I don't know about you, but at the end of an exam problem, when the time is ticking down, I start to get a little bit flustered sometimes. I start to work really quickly, and if I leave all these unit conversion things to the end, I'm probably gonna mess them up, right? Plus, at the beginning of the problem, sometimes I don't really know what to do, so just having something that's kind of familiar that I can sort of fall into the process can help me, right? So my pressure 1 is 340 kilopascals. My pressure 2 is 820 kilopascals, right? Or 8.2 bar. Now, here, we're also told something about the volume. Maybe not as much about the volume as we'd like, but we do know that the volume at state 1 is 0.0283 meters cubed. We don't know the volume at 2, right? But we do know that PV to the 1.2 is constant. We know the mass here is 0.183 kilograms. That's going to be the same. I could put the mass in kilograms up here, right? And it's just going to be the same, right? Because this is a closed system, right? Which means the mass stays constant, 0.183, 0.183. So I know that, right? And the other thing that I know is that the heat transfer, now here's what I'm going to do, because it tells me about the heat transfer, but it just gives me a number. So I'm always just going to write down first what the magnitude of the heat transfer is, right? So we know that this is 2.2 kilojoules. Now I got to think, okay, I know the magnitude, but it doesn't tell me the sign necessarily, right? This could be positive and it could be negative, right? So then I got to think. I know that HIP to win means that heat in is positive, right? But this is telling me, if I look at my schematic here, right? This is telling me that heat is moving, heat transfer from the gas, right? So here, I like to draw heat transfer as like a squiggly line, Q. So heat is going from the gas to the surroundings, right? So that's not heat in, that's heat out, right? So heat out must be negative, right? So really, my value for Q is negative 2.2 kilojoules. So I think for now, we've got all of the given information, right? If not, if we find out as we go through the problem that we're missing something, we can always go back to the statement and look to see if we missed anything. But I think we've got it all, right? Now, it asks us to find the change in the specific internal energy, right? So what we want to find here is delta little u. So specific internal energy, so where I know that mass times little u is internal energy, right? So that must mean that delta little u, which is equal to, the deltas that we're talking about are always going to be at state 2 minus state 1. But this is also going to be, if I could get it, U2 minus big U1 divided by the mass. So that's what I'm trying to find, right? And it tells me that I can neglect kinetic and potential energy effects. So the next part of our process is, what's the governing equation, right? So here we have our governing equation, but we can already start to make assumptions. So I'm going to assume that delta KE is 0, that delta PE is 0. This should be delta SE. I'm going to assume that's 0 too. So the problem kind of told me that, but my advice to you is always going to be write down the whole equation, right? Write down the equation in its entire form, and then you can start to cross things out. Because when you do that, you very clearly demonstrate to me that you know what you're doing, right? That your assumptions are very clear when you do this. So here we're going to say that delta KE is approximately equal to delta PE, approximately equal to delta SE, and they're all approximately equal to 0. Right? So here I can take this and I can say, now this is going to be delta big U is equal to Q minus W. But remember, the problem doesn't actually want me to find delta big U. It wants me to find delta little u, right? So that's going to be M times delta little u is equal to Q minus W, or little u2 minus little u1 is equal to Q minus W divided by M. So this is going to be my equation, right? And this is always the, in thermodynamics, this is the point we want to get to, at least first. We want to get to this point where we have the symbolic solution for the thing that we're looking for. We have an equation that if only we knew all the stuff, then we would be able to solve that equation, right? So over here, now I can start to take account of the things that I know and the things that I don't know, right? So I was told I was told Q, right? Delta little u, this is actually what we're trying to find. So we're not going to know this till the end. We do know the mass. So the only thing left to find is the work, right? Actually, maybe I'll erase that because then I lose the sign, right? So here, oops. Sorry about that. The only thing I have left to find now is work. Right, so I need an equation for work. Thankfully, this is like the second class, and in the first class, we learned an equation for work, right? So we know that work is the integral from V1 to V2 of P dV. Right, so we already did this, we already started to do up here, right? I guess we're also assuming that it's a closed system. Because if it wasn't a closed system, then we wouldn't be able, just writing this equation down, we've already made the assumption that it's a closed system, right? Because if it wasn't a closed system, we wouldn't be able to use this equation, right? But I think we have this, right? So now I can put this in, and if I can find work, then I can get an answer. Right? So now we know that work is the integral V1 to V2 of P dV. Right? We also know that P times V to the power of 1.2 is equal to some constant. So now, what we need to do is we want to put this equation into here. But before we do that, right, so this P has to be P, which is a function of V. So I have to write out P as a function of volume, right? And that's what this allows me to do. But in order to do that, I have to isolate P, right? So this equation here becomes P is equal to some constant divided by V to the power of 1.2. Although personally, when I'm doing calculus, I prefer to write this as C times V to the negative 1.2. So what do? Now I'm going to put this back into here, right? So now my work becomes the integral from V1 to V2 of C V to the negative 1.2 dV. And now this is nice because inside my integral, I have a function of volume, right? Which is pretty good. I know this C is a constant, so I can pull this C out, right? Because it's constant. So this becomes C times the integral from V1 to V2 of V to the negative 1.2 dV. So now I got to remember how to do calculus, right? So what I want to do is I want to add 1 to the exponent when I do this, right? So this is going to be C times inside my bracket. This is going to be V. I add 1 to this, so this is going to be negative 0.2. But then I have to divide over here by this by this same value, right? Negative 0.2, right? And then this is going to be from V1 to V2, right? Notice I haven't put any numbers in yet, right? Because I want to do it all symbolically first, right? So that I have a nice symbolic equation so that if I ever had to do the same problem again, but with different numbers, if I was designing something and changing the volumes around, then I could start to put those values into this same equation, right? So here, this is going to be C divided by negative 0.2 times, I put this is going to be V2 to the negative 0.2 minus V1 to the negative 0.2. Now, this is just aesthetic, but I don't particularly like this part, having to divide by a negative number. So I'm going to multiply this whole equation by negative 1 so that the constant out front is positive. So this becomes C over 0.2 times, now I flip these around, right? Because I'm changing the signs. So this is going to be V1 to the negative 0.2 minus V2 to the negative 0.2. So far, this is my equation for work, right? And there's good news here because I don't know the work, right? But I want this. I want to put this into my solution so that I can get the internal energy, right? I also don't know this constant, right? I don't know V2, but I do know V1. Right? So I've got this one equation that's got three unknowns. Right? So the thing though, I can use this equation, right? Because I know here that P V to the 1.2 is equal to some constant. Right? And that means that because this is constant, it's true at P1. So P1 V1 to the 1.2 is equal to that constant. But P2 V2 to the 1.2 is also equal to that constant. So I got two choices here. I can try to find V2 first, or I can try to find the constant first, right? I'm going to try to find the constant first, but not as a number. I'm going to try to find it as variables, right? And actually, I'm never really going to find it. I'm just going to multiply it in, right? So here I got 1 over 0.2 times this constant times V1 to the negative 0.2 minus, this same constant times V2 to the negative 0.2, right? But I know here that this constant has two different values, right? So over here, I'm going to use the value P2V2 to the 1.2. And over here, I'm going to use the value P1V1 to the 1.2. So this is going to become 1 over 0.2, right? I could just put 5 there too if I wanted to, I guess. P1 V1 to the 1.2 times V1 to the negative 0.2 minus P2 V2 to the 1.2 times V2 to the negative 0.2, right? Now, we kind of did this in a bit of a convoluted way, right? But I did this to show you something because we're going to get kind of a general equation here when n is not equal to 1. I don't know why it always does that, right? So here, if we do this, we'll find that work is equal to 1 over 0.2 times, when I multiply these, remember I add the exponents together. So this is just going to be P1 V1 minus P2 V2. Right? So generally, if n is not equal to 1, right, and I have to do the integral of P dv, it's going to have this same form, that work is going to be 1 divided by, remember, n here was 1.2. So this is going to be n minus 1 multiplied by P1 V1 minus P2 V2. Now, this doesn't work. I guess it also doesn't work if n is equal to 0. If n is equal to 0, pressure is just constant, right? Although that would still work actually here, because this would just be 0 and this would be P2 V2 minus P1 V1, which is what would be the right answer. But if n is equal to 1, the calculus gets a little funny, right? Because you'd get, if n was equal to 1, you would get 1 over v dv. So the integral here would be the natural log, right? It wouldn't be this, right? But we'll do problems like that, I think, in the future, right? So this is generally the equation that we'll get for work if we have n not equal to 1, right? So now the good news is I don't have c in my equation anymore, right? I know P1 and I know P2. I know V1, but I don't know V2. So here again, I'm going to use the fact that I know that P1 V1 to the 1.2 is equal to some constant, which is equal to P2 V2 to the 1.2. Now here again, I actually don't care what the value of the constant is. I'm just going to make this equal to this, right? So if I do that, right, I'm trying to isolate for V2. So here I would get V2 to the power of 1.2 is going to be equal to P1 over P2. So the ratio of these pressures times V1 to the power of 1.2. Or if I want to find V2, this is going to be P1 over P2 times V1 to the 1.2, all to the power of 1 over 1.2. Now, the good news is that now I know, right? This is all known information here, right? I know P1 and P2, and I know V1, right? So I'll give you a second if you want to put that into your calculator, but I did the math over here, so I'm just bringing it up. If I didn't make a mistake in the math, I believe that V2 is equal to 0.0136 meters cubed. Right, so now what I could do with this piece of information is I could come back in here and say that this is 0.0136 meters cubed. Right, and that to me makes sense because here I've got a gas, right? Now, the pressure went up, right? So in order for, if I have gas in this piston cylinder assembly, for the pressure to go up, I've got to push that piston in, right? I'm putting force on that piston to compress that gas, right? So I expect that this volume here, V2, should be less than V1. So I don't know if this is correct, right? But I can't show that it's incorrect. It's doing the thing that I expect it to be doing, right? So that's a good thing. I have some trust in that equation or in that answer, right? So now I want this equation here. So I got to remember little u2 minus little u1 is equal to q minus w over m, right? Because this will actually give me, so now I've got little u2 minus little u1 is equal to q minus w over the mass. Oh, but I still don't have the work, do I? Right? So I was jumping the gun here, right? So I have this, right? But if I did the accounting on this problem, right, I do know the heat, I do know the mass, but I still don't know the work. So I have to use this to find work, right? But that's okay because I've got this equation, right? And now I'm going to take this value and put it up into here. So now I know the value of V2. Right? Once I know the value of V2, I can put that into the work, and I find that the value of work is minus 7.65 kilojoules. I'll show you actually how to do that. I won't skip that step, right? And this, we can see why I did this in kilopascals, right? So here, right, or at least I'll show you the units, right? So here we have our pressure in kilopascals, which is kilonewtons per meter squared, multiplied by volume, which is in meters cubed, right? So when I do this, I take meters cubed divided by meters squared, and I get meters, right? So this unit here is kilonewton meters, right? But I know that a newton meter is equal to a joule. So this is kilojoules, right? I get a negative answer here because the pressure times the volume at the second state is bigger than the pressure times the volume at the first state, right? And this makes sense too, right? Because I know from hip to win, right? So work in is negative. So because in order for us to compress this gas, we're putting work in, right? We're pushing that piston in. So we're the ones doing work. The surroundings are doing work on the system. So work is going into the system. We expect this to be negative, and that's what we get. So just like we thought it made sense that the volume went down, it also makes sense that the work is negative. Right? So now I have a value for work, right? So this is going to be, we had the heat transfer, it was 2.2 kilojoules, but remember heat was going into the system. So this was negative 2.2 kilojoules minus the work is negative 7.65. So this is negative 7.65 kilojoules divided by my mass is 0.183 kilograms, right? So because this is the negative of a negative, that's like adding, right? So here we're going to get 5.45 kilojoules divided by 0.183. Oops, this should be kilograms. Kilograms, right? This makes sense because it's the units are the right units, right? It asks for us energy per unit mass, right? Kilojoules per kilogram, right? And this is going to be, I don't know if anybody's got a calculator. I didn't do this yet. 5.45 divided by 0.183. If I didn't mess up the math, I get that delta U is 29.78 kilojoules per kilogram. Which tells me that the energy at the end of the process is bigger than the energy at the beginning of the process. And I think that that makes sense because even though I'm losing heat, I put more work in than the heat that I lost, right? So that means that the energy in the system should increase. So I don't know if my answer is right, but it does make sense that it's positive. And I got the right units, right? So this is, the last thing we're supposed to do is kind of, does this answer make sense? And I think that it does because, at least as far as we can go, we can't prove that this answer is wrong because we got a sign that makes sense, right? And we got, a number that at least, we can't really say too much about the magnitude yet, but at least we know the sign is right and the units are right. If I got the wrong sign or I got the wrong units, then I would know for sure that I was wrong, right? So here I can't prove that I did it wrong, right? Which is pretty good. So that's the end of this problem. I think the majority of the homework problems this week are something like this, although, they might have different pressure-volume relationships, right? You could see a pressure-volume relationship that's, say, linear, like we talked about, right? And if you get that, what I would do is I would make this a rectangle and a triangle, and I would just do base times height plus base times height divided by 2, right? You could also get, sometimes you'll get this is PV, a constant volume process. Constant volume processes are awesome. This one's a little tricky though, because if you try to do the math, you might get tripped up here as you go from state 1 to state 2. But again, if you draw this out as a PV diagram, you'll notice that that the work is the area under the curve, right? So what's the area under this vertical line? Is 0, right? So if the volume doesn't change, the work is 0 in a closed system. So that, I think, is all that I have for you guys today. If anybody has any questions, we can take them now. Or if not, I'll see you tomorrow.
I have a question. So how did you go from having PV to the power of negative 0.2 times
this part here?
The one right under that one, the one with right under the ones with the red arrows, right above that one. Yeah, how'd you go from having two V1s and two V2s?
So I just multiplied these together, right? So x to the power of 5 times x to the power of negative 1, right? This is going to be x times, or to the power of 5 minus 1, right? So you add these together, right? So V1 to the 1.2.
Oh, I see it.
Right?
Okay.
So this should, I skipped a step here. This is 1.2 minus 0.2, right? And that gives us P1 V1.
So does questions like this will follow this exact same format? If that's the case, I know that we need to do the steps throughout, for the entire points.
But it's nice to know what the destination is, right?
Right, yeah. So if we wanted to find out the work or the answer before doing all the steps for the point, we can just follow this format.
Yep. You do have to be a little careful because it doesn't always work. It won't work if n is equal to 1, or it won't work if the volume is constant, or it won't work if it's not a polytropic process. So if it's linear or something, then it won't work either. But if you have a polytropic process and n is not equal to 1, then I think this equation should work.
How would you know if it's a polytropic process then? Is it because of the PV to the
Yeah, so
power?
anytime this is one of those engineering decoder ring things. So anytime PV to some exponent n is constant, this is polytropic.
Okay. Got it.
Sound good? Thanks for the question. All right. If that's it, I'll see you guys tomorrow.
Thank you, Professor.
No problem.
Thank you.
Have a good one.
Thanks, Professor. See you tomorrow.
See you tomorrow.
See you tomorrow.